Hi, my name is Daniel. I'm a PhD student at the Technical University of Munich. In this work, we investigate the problem of regression testing of multi-language software and how well probe-based system call tracing, which is a dynamic language agnostic program analysis technique, can collect file-level per test execution traces. Our approach can be used to build solutions for regression test optimization, particularly aiming at multi-language software. And our main findings are that first, multi-language software are a relevant problem in regression testing research. And second, ProST, our proposed technique, is efficient and practical. It's easy to use and transfer to other operating systems, and it adds value as it is not limited to analyzing files of a single programming language. Before we start, I want to give a brief introduction into the background of regression test optimization. Regression testing is a software testing activity that's regularly performed on software systems to ensure that changes have not unintentionally affected the existing system behavior. So say you have a program and you introduce some changes, you might want to re-execute your test suite. And the problem is that with large test suites and limited testing resources, this is very prone to be costly and it can be very time intense. Regression test optimization, RTO, tries to reduce the testing effort, for instance, by selecting tests or minimizing the test suite overall. It tries to reduce the feedback time, for example, by prioritizing test cases, for example, with the objective to finding faults early in the process of testing. And it also tries to increase test reliability by providing suitable techniques for flaky test analysis, so reducing the flakiness inside the test suite. And there are several challenges of RTO today, and one particular challenge is multi-language software. On average, or recent studies have shown that in an open source software, on average 5 to 7 general purpose languages or domain-specific languages, and almost 50% of non-code files are present. So this is something that we need to take into account when we design techniques for RTO. The second problem is that we are facing rapid test frequency. For example, at Google, there have been in 2019, I think from this paper is from, there have been 150 million test executions every day in their continuous integration infrastructure. And this raises some problems in the more traditional RTO techniques. That first, they are incapable of collecting per test information, per test traces across language boundaries. And secondly, they often imply an overly expensive analysis overhead in the high frequency CI testing. And we've seen that some companies from industry are moving towards more metadata-oriented approaches that have statistical models, machine learning models trained on some historical information and then use that to prioritize and select tests. Because the more traditional techniques that are based on program analysis are not suitable in those cases. Now, for this work, what we wanted to do is we wanted to take a closer look at that problem of multi-language software and investigate how prevalent that problem actually is in practice. And for this, we first performed an empirical pre-study on multi-language software as a motivation for what we wanted to design as a technique to tackle that problem. And since we know that prior work has already statically analyzed code repositories and found that software projects are on average written in 5 to 7 languages, and that almost 50% of the files in the software project are non-code artifacts, it's important to understand as well what is actually the dynamic behavior of test. So the first motivating research question was, how commonly do projects test across language boundaries, and which combinations of general purpose languages and domain-specific languages are most frequently observed? Because just by the fact that when you statically analyze a repository, there's a source file, there's a Java source file, and there's a C source file, doesn't necessarily mean that testing actually is also done across language boundaries, that we have cross-language links in the software that are also tested. And this is especially not clear because there is some qualitative research that says that testing is especially challenging within the existence of cross-language links. So we do not have the empirical evidence to what degree such multi-language software projects actually test across language boundaries. And the second motivating research question is basically the same, but targets non-code artifact usage. And here we ask, how commonly do projects access non-code artifacts during testing, and which file extensions are most frequent? The experimental setup that we chose was, we went to GitHub, we used the GitHub API and tried to find projects that are multi-language projects. And we did so by using an automated methodology. And we used for projects that we searched for projects that use Maven and JUnit projects that will naturally end up with a project list that use at least one JVM language, typically Java. But then we only considered those projects that use at least one other general purpose language. Why did we use that filter? Well, if we filtered it to projects that use Java plus one domain-specific language, most projects would actually fulfill that criterion, because most projects have, for example, XML as the build system configuration. So we really wanted to see, we wanted to look at multi-language software, so Java or JVM language plus an additional language that's a general purpose language, like JavaScript, C, C++, or Python, or whatever general purpose language. And we used the most popular projects on GitHub that fulfilled those criteria, and we ended up with 25 open source projects, and those were then analyzed by using the Syscall Tracing tool strace, which is very popular, but it introduced a lot of overhead because it's basically running in user space. So all system calls that are being issued to the system, the operating system, are traced, and then in user space, those are filtered to the ones that you're interested in. Therefore, it introduced a lot of performance overhead. But for the sake of this pre-study, it was a suitable tool. And when we looked at the files accessed by every project during testing, we excluded irrelevant files such as log or temporary files that are generated by the test itself, or system and JDK files, because they are beyond the control of the developer, and therefore they are not interested in terms of what kind of cross-language links do actually exist that are being tested. All right, and then let's have a look at the result of this motivating pre-study. We saw that for our first research question, 22 of the 25 projects access more than one language during testing, either another general purpose language or another domain-specific language. The most common combinations for GPL are Java and JavaScript, and for GPL and DSL are Java and XML. And for the second research question, we found that also 22 of 25, not the same ones, you can see it here in this table, access more than one non-code, more than zero, so any non-code artifact during testing. And most commonly, we observed that those were text files. All right, and what is the insight? Well, these results give evidence that multi-language software does indeed pose challenges to regression testing research, as tests do use cross-language links during their execution. And now there are already several approaches to gain insights on what a test is doing during its execution. Mostly, we see code instrumentation techniques used to gain that information, those per test execution traces or per test execution information, also called coverage, test coverage, per test coverage. And those, as I said, can be obtained by instrumenting the code at different granularities. But there is another alternative, and that has become popular because seemingly for regression test selection, file granularity gives very good trade-offs in terms of cost effectiveness. And there is one approach from a paper published in 2017 from Celik et al. They propose RTS Linux, and this is an approach that is using system call tracing to understand what a test process is doing during its execution by tracing process and file related system calls. And this is very interesting because it's language agnostic, so you do not need language specific code instrumentation, but you rather rely on the operating system events that are being triggered by the process. And there's one shortcoming of this approach, though. It's RTS Linux. Linux, the name already suggests that it's used. It can be used on Linux, but it's implemented as a loadable Linux kernel module, which wraps the system call interface. So the shortcoming is it only works on Linux. What about closed source operating systems like Windows? And even if such a kernel modification was possible on Windows as well, our industry partner, I'll talk about them later when I talk about the use cases, they would rather decide against using a modified kernel for maintainability and security issues. So you don't want to modify and then maintain a kernel raise the risk of having some kernel panic in the worst case in your continuous integration infrastructure. So these are some shortcomings, even though the idea is great. And also RTS Linux is currently not publicly available, so we cannot really exactly know what the implementation looks like. But since this idea is so interesting, let's have a look at what we propose as an approach to doing system call tracing to obtain such per test execution traces in different settings than merely on Linux. So the idea is, again, instrument the operating system kernel to trace system calls related to file accesses and process spawns. So we need to know when a process also spawns some sub-process, some child process, and we want to keep track of all the files that have been accessed during the execution of the process, and one process corresponds to one test case that's executed. And here are again summarized the requirements for scalable system call tracing. So what I just mentioned about the shortcomings of RTS Linux, we obviously need to support some more environments and try to solve these shortcomings. So first, we need to support several major operating systems. It needs to be unintrusive. We do not want some custom kernel module that we need to load into the kernel. It has to be lightweight. It must run in kernel space. We've seen that strace, a user space alternative to tracing system calls, is not a feasible option because it just implies too much overhead. And it also has to be stable and secure. We want to avoid kernel panics. It has to be maintainable, and that are the requirements for such a system. And luckily, there are modern kernel observability tools for probe-based instrumentation of the kernel. Two of them, very popular, are dtrace for Windows, macOS, and Solaris. There's also a port for Linux, but that's less popular. And then there is a BPF trace on Linux, which is extremely popular, or in general, the eBPF environment is very popular on Linux recently. And these are all observability tools that have been used over years in production environments at Netflix, at Facebook, and therefore they're really efficient. And luckily, BPF trace uses a very similar API to dtrace, and therefore when we build a tool that's based on those technologies, we can really see that we can reuse parts of the ideas, at least, to implement both or to use them for different environments, for different operating systems. All right, let's have a look at the overview of ProST, of probe-based system call tracing. This is a high-level architecture overview. And as I said, we need to instrument the kernel for system call tracing, but ProST itself can operate in user mode. It acts as a facade to the probe-based kernel instrumentation frameworks, dtrace. We currently use dtrace for Windows and macOS, and BPF trace for Linux. ProST also features a test listener, where we currently have one implemented for JUnit for our experiments. And then we use the information that's generated from the testing component here and from the tracing component to generate the per test execution traces. And here is one sample instrumentation script that should demonstrate the ease of use of these instrumentation frameworks. And here, this is just an example for instrumenting an open syscall on macOS using dtrace, or on Linux using BPF trace. That's the bottom one. And as I said, the ultimate result is the test traces. So for each test, knowing exactly what are the files that are being accessed by that test during the execution. All right, let's get into the evaluation about the effectiveness and efficiency of ProST. To evaluate effectiveness and efficiency, we had two research questions initially proposed. So the first one is, how many more files are actually included in ProST's test traces compared to a language-specific instrumentation? So this basically reflects the effectiveness of ProST. And secondly, how efficient is ProST in terms of introduced execution time overhead compared to language-specific instrumentation? And this is also important when we recall the initially stated problems of RTO techniques, because execution time overhead is something that's really relevant if you have these rapid CI testing cycles, and we cannot really have a lot of instrumentation overhead. For the experimental setup, we use the projects that we also used in the motivating study, and we aim to compare ProST against one established coverage instrumentation tool, and that is Jacoco, because as I said, all the projects have at least one GPL that targets the JVM, and Jacoco, the Java code coverage tool, is a tool precisely aimed at getting the coverage out of such JVM programs. And then there is one, I would say, fairer comparison, which is ClassInst, which is a simple Java agent that is attached to the JVM, and it simply keeps track of the class files that are loaded. And that is basically all the information that any language-specific technique for Java would get at file level. So what are the class files that are loaded? And why is it fairer than Jacoco? Well, Jacoco is a coverage tool aimed at providing statement-level granularity coverage, and this will obviously have a larger overhead, instrumentation overhead, than only looking at the coarse file-level granularity. So this is why we also implemented ClassInst as a fairer baseline here. And as you might have realized, we need to execute every test in its own process to make this work. And this is because the JVM and also other interpreters have some kind of caching in place. And that would mean if we executed multiple tests in a row in the same process, we would maybe miss some file accesses because they're not rereading the file or reopening the file later on when it's again used, but rather they would use their cache, their internal cache of already loaded, for example, class files in the case of the JVM. And that would distort the results. So we fork every JUnit test suite into its own JVM to prevent such caching side effects. And this is something that's common practice in industry, and also in several research papers have already talked about it. Why is it beneficial? Well, in general, to have one test per JVM fork, it will increase your test reliability and prevents having a shared test state that will then maybe lead to test order dependencies, which you might want to prevent. We measure the wall clock end-to-end test execution time and compare the execution overhead against a non-instrumented version of the program. Again, here are the evaluation results. And what we can see here, and I put a little border around it, for the first research question on the left side, we see that ProST finds all files that the language-specific technique finds, and it also finds, on average, almost 90% more files. And in general, this supports prior regression testing research from RTS Linux, where a factor of 5.9 more files were found, whereas we find 0.9 more files. And we expect the difference to stem from the fact that in the RTS Linux paper, no irrelevant system or JDK files or even directories, because Linux will also access directories as files, were filtered out of the set of accessed files. So we expect the difference to come from there. And still, it goes into the same direction. And secondly, for the execution overhead, we find that ProST adds an execution overhead of 4.6% on top of non-instrumented execution. So despite this efficiency, ProST collects all files that were found by ClassInst and Jacoco and an additional 89.2 accessed files. So regarding the results, there are some things to discuss. First, what about the transferability of these results to other language environments and other frameworks, or other tracing frameworks, observability frameworks? Well, system call tracing itself is language agnostic. And therefore, the idea can be transferred to other systems as well. And we've done it for macOS, Windows, and Linux. And though the language environment really can affect the effectiveness, you might think of compiled binaries here. If you compile a C program into one binary and you run that one binary and your test is inside that binary, it doesn't access any other test, you will have exactly one file access, and that's that binary. So this is something that needs to be taken care of, and ProST can still provide a useful extension to existing language-specific techniques because it can consider non-code artifacts. So non-code artifacts that are accessed during testing, and also cross-language links. So if you have some link to a SQL file or something like that, you use that during testing. That's something that ProST will still detect and can be used on top of existing language-specific instrumentation. I already talked about a portability to other operating systems. The concept is portable, and we implemented it for Linux, macOS, and Windows. And we can see by rerunning our experiments for 5 randomly selected projects that the overhead is comparably low on all 3 systems. What are the use cases for ProST? Well, I already said regression test optimization in general. And in fact, we are using ProST already in production today at IVU Traffic Technology, one of our industry partners. And there is a paper at ICSI's site that describes how we're using that for test selection. And you might want to have a look at that if you're interested. All right, let's conclude what we have done in this work. We present ProST, a lightweight approach for probe-based system call tracing to collect file level per test execution traces. And our initial results show that if when you use ProST on multi-language software, we find way more files than language-specific techniques. And also we see that ProST can efficiently extract relevant file level per test information for these systems. So this concludes my talk. Check out our preprint if you're interested. Thank you very much.